Hey everyone, welcome to more calculus talk. We're going to be looking today at Euler's method for differential equations, and this is a numerical method that's going to be used mostly for differential equations that are difficult to solve analytically. So even though the differential equation exists and it can't be solved analytically by antiderivatives, doesn't mean that we can't do anything with it. And this is going to be one of those things, just like the last couple of sections. So let's get headed to it, and we'll take a look at Euler's method. Like always, we're going to be looking at Harry Potter as our context here. So playing on broomstick, Quidditch has the added dimension of altitude. Each team defends 3 hoops atop goalposts set at opposite sides of the pitch. The goalposts themselves are set at 3 heights, 9, 12, and 15 meters. Like in basketball, an offensive player will attempt to throw a ball, called a quaffle, through one of the hoops to score 10 points. So let's suppose that during the first 10 seconds of the match, Harry's altitude changes by a rate of h minus t over 5 meters per second. And at t equals 5, Harry's altitude was 10 meters. Okay, so far we have looked at differential equations analytically, general and particular solutions, and graphically with the slope field. And in accordance to that rule of 3, I don't know if people still remember that, but the rule of 3 means looking at a problem graphically, analytically, and numerically. We're going to be approaching Harry's height with numerical methods. And of course, this means that we're going to be using the information provided to compute Harry's height. So let's start with this differential equation. dy dx is equal to some function m of x and y. So I don't know if you have seen notation for a function of 2 variables, but that's what it looks like, m of x and y, and with an initial condition x naught, y naught. So we're going to use a point slope formula, and in the point slope formula we get this y minus y naught equals the slope multiplied by x minus x naught. And if that doesn't look familiar to you, let me just write that. This is the same as y minus y naught equals m x minus x naught. And that's really what you learned in Algebra 1. Nothing's different here. The only slight adjustment we're going to make is we're going to add y naught to both sides. So we'll get y is equal to y naught plus m multiplied by x minus x naught. Okay. And of course, when you write it this way, you produce a function of y, and that is helpful to us in calculus. So the idea is we're going to add small amounts to the x-coordinate, and we're going to estimate the new y-coordinate based on the differential equation. So this is basically doing a bunch of small tangent lines using our initial condition and our slope field. So when we add a small amount of delta x to the x-coordinate, we're going to produce the next x-coordinate, which is going to be y1, or I'm sorry, x1. So that should make sense. x1 equals delta x plus x naught. And of course, if you want to continue that pattern, x2 is going to be equal to delta x plus x1. So each x is a previous x plus an additional amount called delta x. So if we do it this way, let's see, we can get the next x-coordinate like so. So y1 is going to be equal to the slope multiplied by x1 minus x naught. Now that is this equation again. Y equals y naught plus m x minus x naught. But now we're going to substitute x naught, y naught. So that turns into y naught equals y1 equals y naught plus m x1 minus x naught. Okay, let's see what happens here. And then we're going to substitute after we've substituted. Remember what we said? We said that x1 equals delta x plus x naught. So let's substitute that in here for x1. When we substitute that, we get that y1 equals y naught plus m, and then this is the substitution part, delta x plus x naught minus x naught. Okay, that's the part that we substituted in. And look at that. Plus x naught minus x naught. That stuff cancels out, and we get a really convenient equation. y1 equals y naught plus m multiplied by delta x. Okay. Now, if you look at this equation, sorry, we should write this here. Delta y equals so we're subtracting y naught, so it's going to be m of x naught y naught multiplied by delta x. Okay. So if we call this our change in y, and there's no reason not to call it the change in y, we have y1 equals y naught plus something additional, and of course that something additional is going to be the change in y. So that gives us a formula for the change in y. Delta y is going to be equal to m multiplied by delta x. And this is an equation that's going to drive us here with Euler's method. So this is what the process is going to look like. I would call this one iteration of Euler's method. And really, we've been doing Euler's method with one iteration for quite a long time now, because Euler's method with only one iteration is a tangent line approximation. Euler's method is just stringing together a bunch of tangent line approximations. So here is a curve. The slope field is going to give us this green line here for the tangent line, and we're saying this point right here, that's approximately equal to f of x plus delta x. So since this point, x1, y1, is close to the curve here, and we know it's close because it's a tangent line approximation, we can just repeat the process again. So y2 is equal to y1 plus the slope times x2 minus x1. Okay, and then y2 by definition is y1 plus a delta y. This is still going to be a y1 here, and this del x2, we discussed that already, that's a delta x plus x1. So notice how things fall out of the equation. This y1 cancels with this y1 over here. These x1s cancel out, and we are left with the fact that delta y is again equal to a slope multiplied by delta x. So this tells us again that delta y is equal to a slope times delta x. So this process is going to continue. So just as before, we only need to know x1, y1, and the slope, and a delta x. Okay, so this process that we're going to do is called Euler's method, named after a Swiss mathematician named Leonhard Euler. And pronunciation to help you here, it's Euler, from 1707 to 1783. It's computed in iterations and stops when the desired coordinate has been estimated. So we have a new slope field here. We've got dy dx equals y minus x. Y is equal to f of x, and we're saying f of 0 is equal to 2. So we're going to use Euler's method with delta x equals 0.5, and we're going to estimate f of 2. Now, it doesn't seem like we have much of a method here, but believe me, we do have a method. Here is what we're going to do. Along every point, we're going to calculate a slope. Okay, so number 1, calculate the slope. Once we have that slope, we're going to calculate delta y by multiplying that slope with a delta x. Notice our delta x in this case is 0.5. Once we have our delta x and our delta y, our next point is just going to become x plus delta x and y plus delta y. And then we're going to repeat. So, starting with our first point, 0, 2. First, find the slope. Well, the slope is given by the differential equation. So 2 minus 0 is equal to 2. Now that we have the slope, we're going to find delta y. Delta y is just the slope multiplied by delta x. So 2, which was the slope, multiplied by delta x, which was 0.5 from up here. That gives us 1. Now that we have a delta y, the new coordinate, or the next coordinate, is going to be x plus delta x, which is 0 plus 0.5. Remember, delta x is 0.5 from up here, plus y plus delta y. Remember, y, we started with 2. Our delta y, we said, was 1. And that gives us our next coordinate, 0.5, 3. And then we repeat, and we repeat as much as we need to until we have f of 2. Okay, so just keep on going. First, slope. Slope is the y coordinate minus the x coordinate. Y coordinate minus the x coordinate is 3 minus 0.5. That's 2.5. You may want to grab your calculator at this point. Delta y. That's going to be equal to the slope, 2.5, multiplied by delta x. Delta x is still 0.5. And if I do that correctly, that is 1.25. Okay, here's our notation. Next, x2, y2 is going to be x plus delta x. So 0.5 plus 0.5, which is 1. And then y plus delta y, which is 3, plus 1.25. That is 4.25. Okay, so that's our second iteration. Are we there yet? No. We need to stop when the x coordinate is 2. So we begin again. Let's start now at this new point, which was 1, 4.25. Next step is, or I guess the first step for this iteration, is to find the slope. The slope is going to be equal to y minus x, because that's our slope field from our differential equation. Backwards. That's our differential equation. Y minus x is 3.25. Next, we find delta y. Delta y is the slope, 3.25, multiplied by delta x, which is 0.5. And if you multiply that, let's see what we get. We get 1.625. All right. X plus delta x, y plus delta y. Let's see, 1 plus 0.5 is 1.5. 4.25 plus 1.625, that is 5.875. Are we there yet? No. We need to stop when the x coordinate is 2. So we continue again. Bring down that same, or that coordinate that we got from our third iteration, 1.5, 5.875. Find the slope. Step 2. Slope was x minus y, y minus x from the differential equation, which is 5.875 minus 1.5. That is equal to 4.375. Great. Next, we're going to find delta y. Delta y is m times delta x. M was 4.375 multiplied by delta x, which was 0.5, and that gives us 2.1875. Okay, again, this is a place for your calculator. Last step, x plus delta x, y plus delta y. X plus delta x, 1.5 plus 0.5, that's 2. And then 5.875 plus 2.1875, that is 8.0625. Great. F of 2 equals 8.0625. Okay. So like I said earlier, that's an iterative process. We do the same thing over and over again, producing newer and newer sets of data. Maybe this is a good time for us to take a look at how that looks graphically. So here we are, starting off with our point 0.02 over here. And what we just did is we created a tangent line at 0.02, and we ran that tangent line for half a unit, like that. Let's zoom in here a little bit. There we go. So we ran that tangent line for half a unit, and then that arrived us at 0.5, 3. Okay. From 0.5, 3, we computed a new tangent line using the slope field. That new tangent line looked like this. And then we ran that tangent line for half a unit. And at the end of that tangent line, we've got 1 and 4.25. Then we took that new coordinate, 1 and 4.25, and we computed a new tangent line using the slope field. And that gave us this line. And that ended, we ran that for half of a unit, and that got us at 5.875. And then you guessed it, we did one more tangent line. And we ran that tangent line from 1.5 to 2, x equals 1.5 to x equals 2. And we ended up here at 8.0625. So that's kind of what that looks like with, graphically putting all these tangent lines together. So Euler's method is just putting a bunch of tangent lines together to reconstruct the curve. Now, if you've played any amount of time or with computer things, you know, or you should know, that the smaller you make your delta x, the finer this graph is going to get. And the finer this graph gets, the more accurate your solution is going to be. So if we started doing Euler's method where our delta x's are like 0.1 and 0.01, we're going to produce some high quality predictions without ever calculating a solution to the differential equation. Another thing that we might want to look at over here is how does that line up with the slope field. So here is that slope field, and here are those four tangent lines put together, and you will notice how well it aligns to what we see from the tangent line. Notice that as we go from right to left, from left to right, we go away from the slant asymptote and toward more and more positiveness on the slope. So this is, let's take away those tangent lines and put them together one by one. So we start with our first tangent line right over here. And then we go to our second tangent line right over here. Notice how it's still in line with the slope field, literally in line. Our third tangent line, and then our last tangent line. And that tells us our coordinate approximation. So that's just kind of a graphical look of, what does Euler's equation look like, aside from doing it all analytically. And you can see that it is very much related to that slope field. It does follow that slope field in small increments. So let's try this problem. Suppose that during the first 10 seconds of the match, Harry's altitude changes by a rate of h minus t over 4 meters per second at t equals 5. Harry's altitude was 10 meters. Whoa, no thank you. That's too high for me. Use Euler's method with a t equals 1.0 to estimate Harry's altitude after 10 seconds. So this looks like we're going to have to do 5 iterations. The first iteration is going to be from t equals 5 to t equals 6. Second iteration from t equals 6 to t equals 7. 7 to 8, 8 to 9, 9 to 10. So let's get some calculations going on here. All right. Slope. Slope is going to be equal to h minus t over 4. So h minus t over 4. H is 10. 10 minus 5 is, this is a slope, equals 10 minus 5 over 4. 10 minus 5 over 4 is 1.25. Okay. Next, we're going to figure out delta H. So delta H is equal to the slope multiplied by delta T. So in our case, the slope was 1.25 multiplied by our delta T. Well, that's kind of easy. Our delta T is always going to be 1. So that's going to be equal to 1.25. That's our delta H. Okay. And lastly, we're going to figure out our next point. 5 plus delta, our t is 5. Our delta t is 1. 5 plus 1 is 6. Our h is 10. 10 plus delta h is 11.25. So at t equals 6, we estimate his height being 11.25 meters off of the ground. No, thank you. 6 and 11.25, because we need to get to 10 seconds. The slope, that's going to be equal to, let's see, h minus t, which was 11.25 minus 6 divided by 4. And that number is 1.3125. Okay. Delta H, that's going to be equal to m, 1.3125, multiplied by delta t, which was 1, and that gives us the same, 1.3125. And lastly, we're going to do t plus delta t is 6 plus 1, or 7. H plus delta H is 11.25 plus 3.125. That gives us 12.5625. Okay, again, this is a place for your calculator. Okay, so we're not there yet. So we're going to start at this new place, 7, 12.5625. First thing, figure out slope. Our slope is going to be equal to our h coordinate, 12.5625, minus our t coordinate of 7, divided by 4, and that gives us 1.39062. I have all these calculations worked out already so that we don't have to sit here and watch me fumble with a calculator, but this is just calculator work, okay? And that's kind of the beauty of this. With a calculator, you can solve these differential equations. You can get high quality estimates really quickly. So delta H is going to be equal to M, 1.39062, multiplied by delta T, which is 1. And very nicely, that gives us the same. Last, we're going to do T plus delta T. 7 plus 1 is 8. H plus delta H, 12.5625 plus 1.39062, and that gives us 13.95. That's not enough accuracy. 13.95312. And we ask, are we there yet? No, we're not. We need to continue until t is 10. Next iteration, we're just going to bring down that last iteration, which was 8 and 13.95312. And we're going to figure out the slope. So the slope was the h coordinate minus the t coordinate divided by 4. So that is 13.95312 minus 8 divided by 4. And that gets us to 1.61035. Okay. Make sure you're doing this with your calculator. No one's expecting you to do this, with pencil and paper, at least not like you did when you were in elementary school. Delta H, that's going to be the slope, 1.61035, multiplied by our delta T, which was just 1. And that gives us, well, the same, 1.61035. Okay, t plus delta t, that's 8 plus 1, or 9. And then h plus delta h, that's 13.95312, plus 1.61035, and that's 154414. 140, but I'm just going to leave off that trailing 0. And we've arrived at the last iteration. If you've been calculating this real time, I can feel your pain. This method, incidentally, does really well in programming. If you would like to, in your favorite computer language, create a program that does this, I think it's a great exercise. So slope, sorry, getting back to where we were, slope is equal to h minus t over 4. So 154414 minus 9 over 4. And my calculator tells me that 1.61035. Okay, so I made some mistakes here. My bad. This right here should have been 1.48828. So if you were thinking I was going crazy, you are right. That's what I get for not reading carefully enough. Okay, so that's looking good. 1.61035 for our m. Our last delta h, that's going to be equal to 1.61035 multiplied by our delta t, which was 1 for the last time, 1. That gives us 1.61035. Our t plus delta t, that's 9 plus 1, or 10. Or h plus delta h, that is 15.4414 plus 1.61035. And that gives us 17.05175. Okay. Summary. At t equals 10 seconds, Harry's altitude was approximately, and this number, 17.05175 meters. Okay. So that is Euler's method here. Let's see what we got here. Oh, we got important ideas. So let's get some important ideas. So Euler's method is a numerical method to estimate the particular solution of a given initial condition. Smaller values of delta x will lead to more calculations, but also more accurate estimations. So that's the trade-off. Delta x, very small, more calculations, more time, but a more accurate estimation. So here's a method. I've tried to break this down into 5 steps here. So firstly, you're going to start with the initial condition. Number 2, you're going to use a differential equation to calculate the slope at that coordinate or initial condition, depending on where you are in the routine. Third step, you're going to calculate delta y, which is going to be m multiplied by delta x. And lastly, you're going to find that next coordinate, which is always x plus delta x and y plus delta y. And you're going to keep repeating this until your desired coordinate has been reached. Let's practice this with check your understanding. Suppose the particular solution to dy dx equals xy passes through the coordinate 3, 3. Use Euler's method with 2 steps to estimate the y-coordinate when x is equal to 2. Okay. So first of all, they don't tell you what delta x is, so you're going to have to figure that out. So if we want to get from x equals 2 to we're starting at x equals 3. We want to get from x equals 3 to x equals 2, we need to cover a span of -1 units. Okay, it's going to be, we need to go from from 3 to 2, and we want to do that in two spaces. So that's going to give me a delta x of 0.5. And yes, delta x can be negative. There's nothing wrong with that. All right, so that gives me delta x. Delta x is going to be x final minus x initial divided by the number of steps. That gives me negative 0.5. Okay, so we're starting at 3, 3. That's step 1. 3, 3. Step 2. Use a differential equation to calculate the slope. Okay, the slope is equal to, well, here's my slope field, xy. So it's going to be 3 times 3, or 9. Step 3. Calculate delta y. Delta y is m times delta x. So delta y is equal to m, which was 9, multiplied by delta x, which was negative 0.5. That is negative 4.5. It's negative. Should I be freaking out? No, definitely not. Number 4, we're going to find our next coordinate, which was x plus delta x and y plus delta y. So x plus delta x, that is 3 plus negative 0.5. Y plus delta y is 3 plus negative 4.5. And if we do our calculation, we get 2.5. And let's see, negative 1.5. Okay, and then repeat. Because we're not there yet. We're only at 2.5, and we want to get to x equals 2. So step 1, our coordinate is 2.5 and negative 1.5. Step 2, what is the slope? The slope is from the differential equation. It's x times y. So that is equal to 2.5 multiplied by negative 1.5. 2.5 times negative 1.5 is negative 3.75. Step 3. Step 3 was to find delta y. Delta y is equal to m multiplied by delta x. M, we just found out, was negative 3.75. Delta x is negative 0.5. And when you multiply those together, you've got 1.875. Step 4, that's going to be x plus delta x, y plus delta y. So that's equal to x plus delta x is 2. Y plus delta y is going to be equal to negative 1. You know what I'm going to do? I'm going to write this out a little bit more carefully for you. X plus delta x is 2.5 plus negative 0.5. Y plus delta y is negative 1.5 plus 1.875. And that gives me 2. And let's calculate this. 1.875 plus negative 1.5. That is 0.375. Okay. That's it. We have arrived at the end of the problem. When x equals 2, y is equal to approximately 0.375. So that's it, everyone, with our Euler's method. It's actually a very fast method. I feel like we took it really slow here just for educational purposes. But once you get going here, it goes by really quickly and you can get through a lot of calculations. Just don't forget, you need your calculator here. Otherwise, this becomes pretty unbearable really quick. So that's it. Enjoy. I'll see you guys later. Have a good day.